Today we'll be hearing from, here we go, Arran Gross. So he is in his final semester of his PhD program at the University of Iowa. He completed his bachelor's degree at Rutgers University in New Jersey, and he also has a master's degree at the University of Iowa. While his thesis work focuses on optical and radio evidence of dual AGNs, he has previously also worked with Chandra observations of AGN and X-ray binaries. And today he'll be telling us about variability of accretion sources in the X-ray or in the Galaxy Haro 11. So with that, Arran, feel free to take it away.
Okay. Thank you very much. Let me just get rid of all of the views so I can see what's on my own slide. So as Amy mentioned, most of my research in the past 5 years of grad school is focused on AGN, but I did do a project with one of my mentors out here, Dr. Phil Carrott, and actually a CFA astronomer as one of our collaborators, Andrea Prestwich, about this peculiar Galaxy Haro 11. And I have a very nice recent Hubble image in the background here, and you'll see this image later on, along with a lot of other viewpoints, obviously X-ray most notably. Just to set the stage a little bit, briefly, looking back towards the beginning of the universe, we've got a nice illustration from ESO about progress through expansion. And one question that is still kind of outstanding in the field is just how did the universe change states from cold and neutral back to warm and ionized after the first stars and galaxies started forming during that epoch of reionization. And we have a pretty good idea that you need a source of ultraviolet photons, stuff above the Lyman limit, so that it has the energy to ionize hydrogen. And we have a pretty good idea also that you need pockets of hot, young, bright stars, O and B type stars, like I have in this pretty little picture of, I think, the Rosette Nebula, that produce plenty of that type of emission. But there is a complication to that. So these early galaxies, even though they're not particularly chemically enriched, they are still chock full of neutral hydrogen and some other gases as we get successive star formation. And that's bad news for these ionizing photons that are trying to escape the galactic medium and reach us as the observers. So we know that this gas can absorb that Lyman continuum emission and the Lyman alpha emission, but also neutral hydrogen can resonantly scatter Lyman alpha photons. And that makes it particularly difficult to figure out the origin, the location of where Lyman alpha is really coming from as it just diffuses outwards. So for these photons to be able to reach us as the observers, there need to be holes in the intergalactic medium that form channels of escape so that they don't run into all of this intervening gas in what's kind of been called the picket fence model, where there's slots where the radiation can escape through. So our big question is, what type of feedback do you need to punch holes in a galaxy and allow channels of escape for ultraviolet photons? And then you can have reionization in the early universe. And just as a quick little sketch, we've got our accreting object, maybe it's supernova feedback, like the Crab Nebula, excavates a hole through the intervening medium, and all of a sudden, UV photons are able to escape at some appreciable escape fraction. Now, whether it is a supernova that's generating this mechanical feedback, or maybe it's effects from bursts of star formation, or compact objects with accretion disks and heavy levels of feedback, that's the outstanding question here. So what we want to know is what type of objects cause the sort of blowout that allowed for ionizing photons to escape in the early universe. Now, we cannot spatially resolve distant galaxies, at redshifts of 6, where we know that these types of galaxies originally were. So instead, our strategy is to look for local proxies that we can spatially resolve in the hopes of pinpointing where these types of objects live. To do that, a good starting place is a sample of Lyman break analogs local versions of the Lyman break galaxies that were first spotted at high redshift, which are thought to be those high redshift origins of ionizing photons. And samples from Galax and SDSS from Heckman and Hoops and a couple of other authors that have built on that original sample have looked for local versions of those Lyman break galaxies that are compact spatially, low metallicity, not too much enrichment, very high UV surface brightness. And so overall, we see that they're incredibly bright in ultraviolet and somewhat faint in optical. So we want to build a sample of local proxies that check all these boxes and serve as good local analogs. For my talk, we're just going to be focusing on one of those galaxies from that sample, Haro 11, again shown here. And I actually just saw a paper yesterday that described it as heart-shaped, I guess if you view it from kind of an angle, which I thought was cute. And it checks all those boxes for the most part. I have in quotes that it's low metallicity, certainly lower than stellar, but obviously there are some dust lanes here. And part of that is that this is an ongoing merger. So it's a rather complicated system where parts of it are undergoing intense starbursts, and then parts of it do have some levels of enrichment. We noticed 3 major regions. So this is an older Hubble photo. That newer one has come out since I was writing this paper last year. But there are 3 major regions. Not A, that has the most intense star formation, might be a good place to look for this sort of feedback. Not B, cut through with this prominent dust lane, has the most extinction. It's not much, but it's noticeable. And not C, which also has some levels of star formation, but it's modest compared to these other 2 regions. And so we decided to look for what sorts of X-rays and feedback might be happening in this galaxy using Chandra observations. We originally did a pilot study, and I say we, my collaborators did. This was in 2006, one Chandra observation, well before I had even graduated undergrad. And since then, since this proved to be a rather interesting galaxy, not just in ultraviolet and optical, but in X-ray, we have 3 more follow-up observations to give us a really nice play-by-play of how this thing is behaving over a couple of years. This galaxy is also very interesting because it is one of the closest galaxies that we know with measurable Lyman alpha emission, the sort of ionizing radiation that we care about here, and Lyman continuum emission, slowly leaking out of it. So only one of 3 galaxies, at least at the time of writing this paper, within about 1,000 megaparsecs from the Milky Way, that have these traits, which is to say, this is probably our best shot at really understanding those Lyman break galaxies at high redshift and what they're doing. So we get our Chandra observations, and I'm showing here the stacked version of those 4 different observations in a rather wide band. And for the rest of this talk, we've got not A down here, but there's almost no perceptible level of X-rays. Even though it has the heaviest amount of star formation, certainly evidenced by H alpha shown in red here, it really isn't doing much that we can pick up on in X-ray. Not B, that has plenty of star formation as well, does have a rather extended X-ray source here, shown in blue. So we're going to be focusing on this region, which we'll call X-ray region 1, X1, and then not C, which was, at first glance, unremarkable, is actually the most interesting portion of this galaxy, where we have an X-ray source, we have some star formation happening, but we also have a localized source of Lyman alpha outflows in what almost looks like biconical. So these 2 regions, X1 and X2, for ease of color coding it, I'm going to call X1 the red in the rest of these plots, and X2 I'll color code with blue. And in our stacked X-ray image, we can see that X2 is a lot more compact. So looking at each of those 4 different observations, observation 1, 2, 3, and 4, we have our 2 regions. And it's important for me to mention that these have been aligned we tested several methods, so there is no noticeable astrometric offset between these. And so a couple of things we noticed. First of all, I have this color coded in hard X-rays in green and soft X-rays in red. And even with the first observation, we noticed that these two regions have distinct personalities, spectrally speaking. And those seem to change gradually over time. X2 starts out being mostly soft, but then we see evidence of hard X-rays come into play later on. But also spatially, where these counts are coming from seems to be shifting gradually. And it's not that these sources are moving around, many parsecs over the course of a year, which would be totally unfeasible. It's more likely that sources are blinking on and blinking off. So we've also got evidence of some spatial variability here, maybe multiple sources within each of these regions. Let's start by talking about the spectra. So I'm showing again the stacked versions, again, for counts, a common problem in X-ray astronomy. Do you have enough counts to get a reasonable fit? So we fit these two different regions with a photoelectrically absorbed power law, reasonable for these somewhat gaseous regions that presumably have an accreting source in them. And at a glance, they look kind of similar, but consistently we see that X1 is a bit harder spectrum. It has a little bit more intervening column density, but we're talking 10 to the 20 per square centimeter. That's still not very much. So our best analysis is that this is an intrinsically hard spectrum. Whereas X2, which doesn't have very much obscuration at all, is a rather softer source. So already we've got some distinct differences between these two regions. If we plot what sort of luminosities we get from those regions from our modeling over the course of these 4 observations, and again, there was a big gap between observation 1 and observation 2, and then basically between 1 year and the next for the rest of them. Again, X1 color-coded in red, X2 color-coded in blue. And we see that those regions are doing different things. The X1 region brightens a bit and then seems to drop in flux rather precipitously. X2 brightens a little bit, there's a little dip, and then it brightens to be almost as bright and broadband as X1, the larger region. So we do see some somewhat dramatic changes in the flux over the course of this somewhere around 10-year period. I mentioned also that it seemed like there was some locational variation too. So we did a little bit of a sub-pixel spatial analysis, 2D modeling. And a lot of the images that I've shown you, I probably should have said, but they are at the half pixel size. They've been rescaled to be half the native pixel size. Anything more than that, as tempting as it was to go finer resolution artificially, the advice that we got from the help desk was that the ray tracing at that level becomes a little bit fuzzy. So about a half a pixel is as fine resolution as we can go here. So we would like to know if there are indeed multiple sources in each of these regions flickering on and off. And our strategy, as usual, is to identify the brightest point in each of these regions using wave detect, model it with a 2D Gaussian or a delta function convolved with the point spread, and then subtract it from the model. And then we look at the residuals, we see if there's still some really noticeable bright patches, and we stick another 2D Gaussian on top of that and do the same modeling. I should say that when we use 2, we're modeling it simultaneously on the original image, not on the subtracted. So we're getting a best fit of these 2 point sources simultaneously. And then we look at the residuals, and now we've got within the X1 region, just modeling one region at a time, source A and source B. So that's how I'm going to be referring to these for the rest of the talk. X1A up here and X1B a little bit further down. And hopefully you can see that the residuals only maybe 1 or 2 counts left per pixel without going too far into the negatives. So we run into limitations with our modeling before we get these pockets that are totally artificial negative fluxes. So we do this for the region of X1 for one observation, and we do it separately for X2. And then we do that again for each of the observations. So I know that this is a lot to show in one slide, but the gist is that we see a similar pattern across observation 1, 2, 3, and 4 to the X1 region, and then a similar pattern for the X2 region, where 2 sources in each gives a much better fit. And since we're doing this fitting with cache statistics, it's very easy to translate that into a likelihood ratio, whether or not 1 source per region is better than 2 sources per region. And in all cases, in each of these fits, having 2 sources per region is justified statistically at about the 95% confidence level. 3 sources, absolutely out of the question. That you do not get a statistically significant increase. So we stick with 2 sources, although the residuals indicate there's likely an ensemble of objects in each. Doing the same sort of flux modeling, this is similar to the one that I showed before for just X1 in red and X2 in blue. But now let's split it into a primary and secondary component, X1A in red and X1B in pink, which hopefully is similar enough in color. And we see a similar pattern with the primary sources where they kind of brighten a little bit and then they dim. And it's in those later observations where the secondary sources, which are almost undetected at first, start to brighten and even overtake the primary source in each region. So we end up with the dynamic system where we've got at least 2 X-ray sources, most likely in each of these regions, that are dimming and brightening at different periods. So we've got a whole bunch of evidence now, spatial, spectral, flux-based, that there's a lot of variability in this galaxy in these 2 X-ray regions. And we're going to try to piece that together to figure out what kind of sources of X-rays are going on here. What's causing all of this variability? And the short answer is it's probably some sort of compact accretion-based source. Could it be an X-ray binary, a stellar mass black hole being fed by a companion star nearby, generating the accretion disk? The sort of signature we would expect here would be that it would be in a low, hard accretion mode, and we would expect a harder X-ray spectrum. Similar to an X-ray binary, we might have a pumped up version, these recently discovered ultraluminous X-ray sources, where we've got a black hole that's reaching Eddington level or even super Eddington level accretion, and then we get radiation pressure generating a mechanical feedback, blowing out intense winds of material. The signature that we'd look for this one really depends on the viewing angle. If we look right down the barrel of the jet in this cross-sectional figure here, we would still expect a similar signature as we did in a normal run-of-the-mill X-ray binary. It would be a relatively hard spectrum. If we've got any angle of inclination that looks into these winds that are blowing off, all of a sudden we might be looking through some comptonized corona being blown off the disk, and we would expect a softer spectrum. One more possibility, scaling this up even further, could it be a supermassive scale black hole generating an active galactic nucleus? In this case, I turn to one of the tools of the trade for optical astronomers, the Baldwin, Phillips, and Turlovich diagram here, that looks at optical emission line ratios to see what sort of cause of ionization is going on. And it's broken into these 3 distinct regions. And if we plot the whole of Haro 11 using slit spectroscopy that goes over the entire galaxy and do it as one whole ensemble, we see that it falls in the starbursting region, that the source of ionization is likely from starbursts. nothing too surprising. We know that it's making new stars. If we look at the regions of X1 and X2 individually, they start to drift more towards this composite region where there's definitely evidence of starbursts ionizing the interstellar medium, but also probably some contribution from a central accretion source, probably an active black hole. Just for reference, I have a bunch of other similar galaxies plotted here from the literature, other galaxies that emit Lyman alpha, Lyman continuum, but none that are as nearby as Haro 11. Okay, so with those three options in mind, let's just piece together the evidence that we have from the different modeling. Starting with X1, we know it's got a harder spectrum, possibly evidence of an accretion source with jets. It is slightly more obscured, and there are dust lanes, but it's really not that much obscuration. This is the brighter of the two regions. So at that point, it does start to cross over into the regime of maybe a low luminosity AGN fueled by an advection-dominated accretion flow, or perhaps it's several X-ray binaries in that low hard state, all contributing to this ensemble X-ray flux. In X2, we see something distinctly different. It's got a softer spectrum. Maybe we're looking at winds from an accretion source. It is more ionized with a lower column density, and it's a little bit fainter. But if we model how much expected X-ray luminosity we would get from an ensemble of X-ray binaries using this relation from Mineo et al., just pushing through the H alpha luminosity for this region, we would expect X-ray binaries to contribute about 10 to the 38 ergs per second luminosity in the X-rays, 2 orders of magnitude lower than what we actually see. So to explain this, we think it's either X-ray binaries, but most likely one individual ultraluminous source that can actually produce this level of X-ray radiation. I know I'm stretched for time, but I'll briefly mention star formation and starbursts can also generate mechanical feedback that could be responsible for these sort of blowout scenarios. But is it enough? If we're looking just at this X2 region, this has a much lower star formation rate than the X1 region, to the level of something like 1/10 of a solar mass per year. And we know the current age of that starburst. It's not that new. So modeling it with the Starburst 99 code, we see that the mechanical feedback from a starburst starts to drop off. And at the current age of that part of the cluster, it is still pumping out a lot more X-rays than can be explained by star formation effects alone. At this point, we think, putting that all together, that that X2 region is probably hosting an ultraluminous X-ray source. X1, even though it's brighter in X-ray, doesn't have any Lyman alpha leaking from it. It probably is generating plenty of Lyman alpha and other UV photons. And the hard spectrum suggests that it probably hosts several X-ray binaries. So why are those ultraviolet photons not able to escape that portion of the galaxy? And putting all this together, our conclusion is that the major difference between these two regions and why not C, the X2 region, has Lyman alpha escape, the clear deciding factor is that it hosts an ultraluminous X-ray source. And it's that Eddington level accretion and that mechanical feedback from winds that are blowing out channels and allowing that Lyman alpha to escape. And that might be the major ingredient in these early galaxies, allowing for the epoch of reionization. I know that that was a very, very broad overview, but if you are curious, this paper is in press and I invite you to read it. And with that, I'll take questions.
Thank you, Aaron. That was a great talk.
Thank
So I haven't seen any questions in the chat, but if anyone has any questions, feel free to raise their hand. I'll look through the list here. So maybe while we're waiting for a question or two, we can ask, you're writing your thesis. What's up next for you? Are you going to continue along this line of research or?
You know, it's interesting. This paper is kind of a one-off side quest. And my actual thesis advisor was on sabbatical at the Keck telescope in Hawaii, right when the pandemic started. So this project came along from Professor Phil Carrot, and he had some funding lying around. So we thought it would be a pretty fun thing to use up for a semester. I would love to do more investigations along these lines. And in fact, I think there's a lot in the eRosita survey that you could use some of these lines of reasoning to look for more ULXs and certainly X-right binaries and see if there is a definitive link between those objects and Lyman alpha emission. But as to my thesis, it is optical spectroscopy, radio interferometry imaging of, my joke thesis for my title so far is double black holes from rainbow and radio. But no, I would certainly love to do more investigations along this line.
Seems like a very interesting project, one that you can certainly continue on. So I don't see any other raised hands at the moment. Oh, okay, we have one in the chat here. 10 said, you mentioned that this was a low metallicity system. Is there any evidence for metallicity differences throughout the galaxy?
Yes. I'll preface this by saying that that is not the legerdemain of my X-ray studies on this object. That is purely from archival optical studies. And this galaxy has been studied in optical a lot more through different kinds of spectroscopy, some very rudimentary integral field unit spectroscopy. But through that, we noticed that there are metallicity differences. That region of not B with this dust lane, dead ringer, it's more enriched. But you know, as far as whether it's a tried and true proxy for these Lyman break galaxies at high redshift, whether or not Haro 11 really is low metallicity enough to be a good comparison, that's something I kind of sweep under the rug. I would say it's on the cusp. It is certainly very much subsolar. I've seen quoted that the galaxy taken as a whole is somewhere around Z of 0.009. But it's complicated because it's undergoing a merger. So it probably absorbed a galaxy that was very low metallicity into a galaxy that had already been enriched. So that's why we get these very different pockets. I hope that answers your question.
All right, thank you. I don't see any other hands up in the chat, so I think we're about on time to move on to our next speaker. So thank you, Aaron.
Thank you.
So our second speaker is Tim Linden from the University of Stockholm in Sweden. So Tim got his PhD at UC Santa Cruz in 2013, and then he did a postdoc at University of Chicago of 2 years. And then he was at the Ohio State University for 5 years. And since 2020, he's been an assistant professor at the Stockholm University. Today he's talking about a very interesting timely topic, which is evidence for a new component in the solar gamma ray emission. So we are very happy to have you here, Tim. Please, the floor is yours.
Great. Thanks so much for having me. It's great to chat with you on at least a virtual environment, and hope to be able to visit at some point in the future. So if you're not stuck in Stockholm for the last few months of May, like me, you normally think of the sun as something like this, a bright, overwhelming source in the sky due to its proximity, which not only dominates the optical sky for some number of hours a day, but also dominates the local medium, the magnetic fields around the solar system, producing things like termination shocks, producing outflows of charged particles, and dominating really the magnetic field throughout, all of the region that we've yet personally been able to send spacecraft to or anything like that. The sun produces its own flares of charged particles moving out, solar flares, coronal mass ejections, charged particles that we certainly care about for a number of reasons when we think about, astronauts or manned missions or disruptions to satellites and things like that. But if we look instead in gamma rays, we see that the universe and the sun, daylight or in the middle of the night, looks something like this. There's no sun there that's dominating the gamma ray emission across the universe. Now, this is a little bit of a tricky way of looking at it because the sun actually moves through this coordinate system. So the solar gamma rays, unlike everything else here in RA and declination, is smeared out quite a bit. And actually, the sun is the 30th brightest gamma ray source in the sky at an energy of a few GeV, which is the standard Fermi-Lat energy range, which you should think of for the purposes of this talk. Now, that is personally very interesting to me. It's 10 to the 24 times intrinsically dimmer than the standard galactic sources like Vela, Gaminga, or the Crab, and 10 to the 24 times closer in D squared. And those things actually cancel to about a factor of 5 or so. So why would we look in gamma rays to try to see the sun? It is not hard on the average day to spot it in a bunch of different wavelengths. That's because gamma rays can tell us interesting things about the physics of the sun. The magnetic fields that are producing things like solar flares or coronal mass ejections. We can learn something about what is happening below the solar surface when it becomes optically opaque, but in a region in which gamma rays can transfer through. And we can learn about the cosmic ray outflows and things that are producing radiation, solar radiation at Earth. How are solar gamma rays produced? Well, it's not due to some sort of, thermal mechanism like we expect for solar physics. The sun has a temperature of 6,000 Kelvin, which is about half of an EV. For gamma rays at about a GeV, this emission would be suppressed by e to the 10 to the 9 or something like that. So this is not an emission mechanism for solar gamma rays. Instead, we need some other way of accelerating particles to relativistic energies to produce gamma ray emission. Now, the sun can do that. It has strong magnetic fields. It has those magnetic fields are quickly moving across the solar surface. There are reconnection events where particles can be accelerated in these loops, and you can get magnetic fields here, particle acceleration here, and then these solar energetic particles, move through the solar system, potentially encountering Earth. And this is a very bright emission source at low energies. So here is the sun during a bright solar flare compared to the rest of that entire sky. And you can see here for this, few hours, the sun was the brightest source anywhere in the universe of gamma rays. But these are 100 MeV gamma rays. And actually the highest energy gamma ray ever observed from the sun, from a solar flare event, is at 4 GeV. This is not what I'll be talking about today. I need more powerful gamma rays. I need high energies and I need bigger accelerators. So let's go and see what makes the highest energy cosmic rays, the GeV, TeV cosmic rays that we know of from things like supernova remnants or pulsars. And let's see how those interact with the sun to produce emission that maybe we can see. So here is the cosmic ray spectrum from protons and all particles, and you know that this continues all the way to ultra high energies, somewhere around 10 to the 10 GeV or something like that. Now, these cosmic rays travel from those sources and they bounce around the interstellar medium, and eventually they make it into our solar system. Sometimes they get picked up directly as cosmic rays by experiments like AMS, and sometimes they produce gamma rays along the way to be picked up by something like the Fermi-Lat telescope. Sometimes they make it into our solar system, but they don't hit our telescopes most of the time, but instead they interact now with the solar environment. This can produce gamma rays in two ways. The first is through inverse Compton scattering. When a high energy electron makes it into our solar system, it can hit the starlight from the sun, which is quite bright, dominating the local radiation density, and produce gamma ray emission through an inverse Compton process. The profile of that falls off as you go farther and farther away from the sun as 1 over r squared, because that's how the solar density drops off. But there's a second mechanism from the solar disk itself. When a high energy cosmic ray proton comes in, it hits the gas on the sun, and that produces a hadronic interaction, just like at a particle accelerator. These high energy cosmic ray protons come in, they hit protons, and they produce showers. And those showers include pions, muons, neutrinos, and gamma rays. Now, if you think about the sun without a magnetic field, the scenario would look something like this. Cosmic ray protons would come in from every direction. They would hit the solar surface, and they would produce showers. And those showers would typically go inside the sun, where they would be absorbed by all of the dense solar material. You would only see these gamma rays if they happen to hit right on this edge, where the optical depth is about 1. There you could get a single interaction, produce 1 gamma ray, and that gamma ray could move through the rest of the solar, the edge of the solar surface without interacting again and make it to the Earth. You would see something like this. This is what this would look like in the Fermi-Lat telescope. This is E squared dNdE, the energy flux. This is the Fermi-Lat sensitivity, and this would be that limb emission just from the edge of the sun. We would probably have seen it by now, but it would be difficult. Way back in 1991, Sekal, Stanov, and Geiser put together another mechanism. The sun does have magnetic fields. So a high energy cosmic ray could come in, turn around in those solar magnetic fields, and then on the way out, while it's leaving the sun, interact with gas and produce a gamma ray that is now outgoing and can be observed at Earth. This requires a really Goldilocks tuning. If this cosmic ray goes in too far, it dies on the way in before it can turn around, producing an ingoing gamma ray that can't be seen. If it turns around too early because the magnetic fields are strong, it never encounters any gas, so it doesn't produce a gamma ray at all, and we don't see the emission. Only if it turns around right about when the optical depth is 1 can we see an appreciable gamma ray flux. And we note there are many different regions over the solar surface where the magnetic field strength is very, very different. To produce GeV gamma rays, we need to be able to turn these cosmic rays around at about 100 kilometers in depth. That's about where the optical depth is 1. And so to do that, we need regions where the magnetic fields are enhanced, such as in solar flares, in these sort of flux tubes that proliferate along the surface of the sun. But still, because it's now not just the edge that's bright, but the whole solar surface can participate in these events, the SSG mechanism, as it's known, predicts a brighter gamma ray flux, at least at low energies. In the 1991 model, they assumed that at about a gamma ray energy of 5 GeV, corresponding to about a 100 GeV proton, this mechanism would no longer work. The protons would have too much energy, they would go too far into the sun and produce ingoing gamma rays, and those would no longer be seen. So they expected a cutoff about here. Now I want to talk about 4 papers from our group at Ohio State. The first one I'm not on, but the last 3 I've been working on with collaborators there and now at Stockholm as well. And these all take advantage of the same idea in looking for gamma ray emission from the sun. The sun is moving across the galaxy compared to everything in the static background, and we can use that to our advantage. Basically what we do, there's a lot of different mechanisms in the different papers, but they all take advantage of this fact. What you can do is look at the entire universe on one day when the sun is in one part of the sky, and then look at it 6 months later when the sun is in a different part of the sky, subtract those images, and you get back the gamma ray emission from just the sun. You do that at the position of the sun, shift every single gamma ray event to both its astrophysical position and its solar position relative to the sun's center at that time period. And you difference those images, and you can get rid of all of the bright gamma ray backgrounds. So you start with a map like this at 100 MeV up to 300 MeV. You subtract the background and you get left with just this, just the sun at the center and nothing else in this image. Here's the same thing from 3 to 10 GeV. Here's the full sky. These streaks are really bright point sources. This is, I think, is actually the Crab Nebula moving past to the sun. And then you background subtract it and it goes away entirely. Now we did this and we found that everything we knew was wrong. The first thing we found, dating back to 2016, before I actually started on this project, was that the gamma ray intensity was even brighter than predicted by the SSG model. So here's the SSG prediction here in gamma ray intensity. Here's from the Fermi-LAC collaboration in 2011, a model up here. Here's our calculation of the emission from 2008 to 2016. These are consistent because the sun is variable. We'll get to that in a minute. But you can see this is still several times more efficient than produced by the Stanil-Stekeman geyser mechanism. And even more so, if you extrapolated this mechanism and didn't assume a cutoff, it becomes much, much brighter at high energies. This spectrum remains really hard. And that's weird because we know that the cosmic ray spectrum that is producing these events falls as e to the minus 2.7. All of our cosmic ray observations on the ground from experiments like the alpha magnetic spectrometer all tell us that the gamma ray spectrum falls as, the cosmic ray spectrum falls as e to the minus 2.7. And that means, from knowing particle physics and colliders or something like that, the gamma ray spectrum also must fall as e to the minus 2.7. Instead, we see that the gamma ray spectrum is about approximately e to the minus 2 or e to the minus 2.1. And that continues over a few orders of magnitude. In a more recent observation, we pushed this to both lower and higher energies and found that this is remarkably consistent. So here is the gamma ray spectrum of the sun now from 2008 up to 2020, e to the minus, I think, 2.05 over 3 orders of magnitude in energy. Moreover, the sun is highly variable as a source. We see here the flux in 2008 between an energy of 100 MeV up to 1 GeV, or 1 GeV to 10 GeV. The flux in 2008, 2009, 2010, this is the period of solar minimum activity. And then it falls off precipitously towards solar maximum by more than a factor of 2 per year, and then slowly climbs back as we get into the next solar minimum cycle. It is inversely proportional to solar activity. And we have great knowledge of this 11-year solar cycle over many, many periods. And so we can guess what might be happening here, right? When during solar maximum, the magnetic fields are very choppy. This probably prevents cosmic rays from moving in close towards the solar surface because the magnetic fields are very twisted. And then maybe during solar minimum, the magnetic fields are smooth. Everything is maybe a little bit more less turbulent, and the cosmic rays can penetrate more reasonably. However, this doesn't really make any sense in the standard picture of solar modulation, because in that picture, this should be a highly energy dependent phenomenon, right? Low energy cosmic rays respond very strongly to solar magnetic fields, where higher energy cosmic rays barely see them at all because their rigidity has is very high and they have a very long path length. Instead, we see that the change in the flux as a function of time is basically energy independent. We look for variability on all sorts of other scales, using the vast amount of data to probe the power law of variability on scales going from just a couple hours up to the entire lifetime of the mission. We looked for variability at a 27-day scale that corresponds to the mean solar rotation, and we didn't find anything there. We did find a few peaks of variability. This is half a year from the crossing of the plane. This is the quarter year harmonic of that, the third of a year harmonic from that. This 46.2 days is an instrumental rocking angle adjustment. And this 1 day period is not quite explained, but it is exactly 1 day. It probably has something to do with the Earth. So we saw no other signs of variability except for this 11-year period that corresponds to the solar cycle. Then we looked at the morphology and became even more puzzled. So this is a complicated plot, but I'll try to talk through it carefully. These are events from 10 to 50 GeV in energy, so very high energy events. And we focus on very high energy events because this point spread function, the angular resolution of the individual events, becomes smaller than the size of the sun, which is this inner circle here. The outer circle is the ROI that I'm looking at. So this is the sun. This is the average uncertainty of these events that are recorded here. This is between 10 and 50 GeV during solar minimum. This is above 50 GeV, also during solar minimum. This is 10 to 50 GeV after solar minimum. This goes up to 2017, so this is all solar maximum. And this is above 50 GeV during solar maximum. You can see here a histogram of these events observed in solar latitude compared to an orange line, which is an equally bright sun. So if every point on the sun has an equal surface brightness. During solar minimum at 10 to 50 GeV, the sun looks like it's about equally bright. The polar flux is about 13 in these units. The equatorial flux is about 12. These units don't actually matter. But you go to higher energies at 50 GeV, the equatorial flux becomes 4 times brighter than the polar flux. There's a huge bright line of gamma rays produced right across the solar equatorial plane. There is a north-south asymmetry that leaps out to your eye. It is less statistically significant once you fold in the uncertainties of these different events, which are all taken individually into account in our formal fitting. Here is solar maximum. What you see is a deficit along the equatorial plane. We're missing events here, right at the center, compared to the equally bright sun. The polar flux actually stayed the same, 13.1 to 13.9. The equatorial flux dropped by a factor of 4, and this became polar dominated. At 50 GeV or higher, the equatorial flux just disappears. The polar flux, again, stays the same, 5.7 to 6.4. The equatorial flux drops by about a factor of 40. So there's a new equatorial emission component that is bright during solar minimum and not bright during the rest of the solar cycle. Here's the same thing, recalculated. This left-hand plot is the same as the solar minimum from before. The right-hand plot is the new solar minimum during cycle 25. Again, we see basically the same behavior. The polar flux and equatorial flux are equally bright during the new solar minimum. And the emission is primarily equatorial at energies above 50 GeV, while the polar flux appears to have, is still about a factor of 3 or so dimmer than the equatorial flux. We do see that during this period at the highest energies, the total emission flux from the sun is slightly less bright than during the previous equatorial solar cycle at the highest energies, or previous solar minimum at the highest energies. On top of that, we see 8 events with energies above 100 GeV, all taken during solar minimum. So this is 2008, 2008, 2008, 2009, 2009, et cetera, et cetera. Then we had a 7.5-year hiatus where no gamma rays were observed above an energy of 100 GeV, compared to an expectation during those next 7 years of 40 or 50 events based on this flux here. The sun can apparently only produce gamma rays above 100 GeV across its equatorial plane during solar minimum. And that corresponds to 2 TeV protons that are being turned around by solar magnetic fields, something that was never thought about in the SSG models. So putting this picture together, we now get something that's actually the weird part, I guess. We plot the flux during solar minimum, and it looks like this, and it looks like this, and it looks like this, and it looks like this in e to the -2, and what? The flux drops off by a factor of about 4 at 8.9 sigma for an energy range of about 20 GeV, and then comes right back up and becomes e to the -2 again, up until an energy of about 200 GeV or so, where then we run out of photons. This is essentially impossible to model. Nobody, I think, has come up with anything convincing. And a way to explain why it's essentially impossible to model is, let's pretend you have the perfect proton spectrum to produce the emission you want, which is basically to say you have a bunch of protons, and then you have 0 protons, and then you have 0 protons, and then you have a bunch of protons again. So you just make a step function where you cut out all of the protons that would produce the gamma rays at about 30 GeV where there's a dip. Well, you can't do that because particle physics says that the kernel of producing gamma rays from protons is very, very broad. Yes, you want to get rid of the 200 to 300 GeV protons to get rid of the 20 to 30 GeV gamma rays. But getting rid of those also gets rid of 1 GeV gamma rays, and it gets rid of 100 GeV gamma rays. And it's very, very wide here. Well, what we observe in data is extremely sharp. there's no way to get both this depth of a factor of 4 and at the same time get this to be as narrow as this dip actually is by getting rid of protons in any configuration that you want. And so putting the picture together, we see that, nothing here makes any sense. And that is how I should close my talk, but I will take a few minutes to try to come up with something to model and just show how difficult this really is. And it's difficult because it's so bright. The sun is so much brighter than the SSG mechanism. It's so much brighter than the disk limb. And you could calculate this gamma ray flux as something that kind of looks like this. It's pi r squared of the sun, okay, that much is obvious, times the flux of cosmic rays. Well, we have measurements of that from AMS at like the 0.1% level, what the cosmic ray flux is. We do know that number. Times the energy of, the flux of cosmic rays at some energy, times some convolution function that tells us how a cosmic ray of a given energy produces a gamma ray of a given energy. Well, that's known from particle accelerators at like the 1% level, right? You have a cosmic ray of so-and-so energy, it hits gas and it produces gamma rays. We know that function. And that's basically it. The only thing I can change now is some survival probabilities. F surface, which I'll say the fraction of the solar surface that is participating in producing gamma rays when it gets hit by the sun, that can be from 0 to 1. F turn, the fraction of cosmic rays that turn around before they die inside the solar surface so they can produce outgoing gamma rays. And F interaction, the probability that my now outgoing gamma ray interacts to produce, or outgoing cosmic ray interacts to produce some gamma ray that I care about. These are all efficiencies. They should all be between 0 and 1. If they are all exactly 1, this is the line I expect, the maximum solar disk emission. And you can see the gamma ray flux, and during solar minimum, is this blue point here is getting very, very close to this maximum solar disk emission line at these highest energies. And it appears to be continuing in this direction with no signs of cutoff, while the flux from the maximum solar disk emission should be falling z to the minus 2.7, because that's what the cosmic ray flux does. So what this tells you is that nearly every cosmic ray that hits the sun turns around at exactly, this isn't even tau equals 1. Tau equals 1 means you lose 1 over e of the events before they turn around. That's what tau equals 1 means. And if tau is less than 1, you can't produce cosmic or gamma rays from your cosmic rays because they don't encounter any gas. So that makes F interaction 1 over e or something like that. These functions, F turn and F int, can't both be 1 at the same time. That simply doesn't make any sense. But even if all these things are maxed out, you can't get everywhere. So almost all of the sun has to basically have a mirror at the very perfect point. Cosmic rays are paying a ticket where they're like, am I at the right point to maximize the gamma ray flux? Okay, let me turn around right here and produce the gamma ray flux going outwards. And then you will just get as much emission as we see. So here's, remember on these plots, what the cosmic ray spectrum is doing. And it is supposed to fall very, very fast. Now, we wanted to continue following this up in Fermi, and we've done that. There was a status update in 2018, a month after we put out the big paper on the 2 solar emissions, where there was a problem with the solar panel on one of the solar panels on the Fermi lat. And that caused them to change their configuration so that solar panel is now physically pointed towards the sun by rocking the whole instrument. And unfortunately for us, that means that when that solar panel is rocked towards the sun, the telescope part is not rocked towards the sun. And so that has cost us about a factor of 5 in solar observations over the last few years and made it more difficult during this current solar minimum. But there is hope in the 1 minute that I have left with the Hawk telescope, which is a high energy water Cherenkov telescope. We looked for gamma rays now at energies of 1 TeV during solar minimum or solar maximum, when we didn't expect 1 TeV emission because we didn't see 100 GeV emission during solar maximum with Fermi. And we haven't seen anything, but we did put really strong upper limits on this data set here compared to this gamma ray emission here. And so we can see during these blue points that are solar minimum, if this emission continues, then as we reanalyze these last few years of solar minimum, with the Hawk telescope, we should see bright emission. Stay tuned. So to conclude, we see, but we don't understand. We need help from theorists to make any sense of these observations. And if we can do that, solar gamma rays provide a new handle into the fundamental questions of solar magnetohydrodynamics. Obviously, they don't work like we expect, and that's extremely interesting, especially for beings here on Earth. And there's a huge potential here. I just want to note for other people interested in solar physics in general, for cross correlations with other wavelengths. We have nearly continuous, or 1/6 of all the time observations of the sun over 12 years, and we would love to correlate that with what's being seen by other astronomers. Thanks.
Wonderful. Thank you so much, Tim. It was really hard to stop you, even if you went a little bit first time. I'm sure that many people are as puzzled as I am by these observations. So let's see if you have any questions here. I don't see no question. So maybe I can ask something. So this SSG 91 model is clearly not able to explain even the low energy emissions. So what about a possibility of connecting the explanation of the deep with the two different components? So is there, for example, any attempt to use any sort of exoteric dark matter scenario to, for example, trace back the high energy part, which I assume will be more likely the one due to the dark matter?
Yeah, as somebody who loves to make up dark matter explanations for things, I'm certainly not shy in that regard. I think dark matter explanations here are difficult. And the problem is, why the sun and why with this luminosity? You would need a dark matter particle that accumulates very efficiently in the sun and produces very bright outgoing emission, but then doesn't do that in any other astrophysical object that we know about. Objects that are way denser and thus attract more dark matter, or in much more dark matter rich environments, are in much larger regions where gas densities are high and things like that. We weren't able to think of any convincing model that would produce gamma ray emission. And the second thing that would be weird from a dark matter explanation is it really has to sit right at the surface of the sun, right? No matter what you do with the dark matter, once it produces gamma rays or something like that, they get absorbed if they go through too much solar material. And the same is true of any other charged particle that you would want to produce with dark matter. So you need them to just kind of sit at the solar surface, a dark matter particle with a wavelength that's exactly one solar radius or something like that. It was very hard to come up with something. This is actually a funny story because there is a YouTube video that was made by somebody who believes the sun is a liquid. But also they were criticizing our paper on the sun, and they said that dark matter, we just make up dark matter explanations for everything. And I think this is one of the few papers where I have no dark matter model that would possibly produce this. So yeah. I think that's hard. On the other hand, you are right that like a spectrum that rises this steeply is something that always makes dark matter or new physics people interested, because it's really hard to do with astrophysics.
Thank you. So let's try to go quickly. I see a question from Jay Sub, please. Go ahead.
Hi, it's very interesting talk. I wonder, I guess this spectrum is, I guess, average spectrum. Then if you consider that the solar cycle modulation at the high energies, is this already violating CP cosmic ray upper bound? So that's first question. And second question is, this is a little bit off topic, but if I remember correctly, long time ago, I remember reading the text saying, in terms of gamma ray, actually moon is more bright, but given this new sort of measurement, I don't know you have any information about the sun is more bright in gamma rays compared to moon or not?
Yeah. So for the sun versus the moon, it's the totally energy dependent statement. The moon is a brighter source at about 100 MeV, but the moon spectrum is about e to the minus 3.5. I don't have the right plot for this, but the moon spectrum, it comes down like this very rapidly. And there's no moon emission above a GeV. Your first question was, are we already violating the cosmic ray upper bound?
Yeah, if you consider during the maximum cycle, if you just compare the spectrum during that time, is that the case, or is it?
So this is the solar minimum, the maximum, right? Solar minimum emission right here. So this is the maximum, and you can see, I mean, if you took the low end of this error bar, we could still be a factor of 4 or 5 away from the saturation point. You know, we need a couple more data points here, or we need to really narrow these error bars to try to track that down.
Thank you.
But, you know, I think naively, if you tried to calculate what these efficiency factors were and had no idea how bright you know, you would expect most of these efficient factors to be 10% or 1% or something like that. The fact that they're all order 1 is odd.
Thanks. John.
Hi. I was wondering, at least for the low energy part, if the magnetic field is strong enough to turn the particle around, it's also strong enough to trap it. Can you imagine any kind of magnetic topology in which particles would come in and get trapped and therefore be much more efficient in producing gamma rays?
Yeah, that's a great question. It is something we've considered, and something where I am not the level of expert on solar magnetic fields to really come up with a good model for it. But, you know, one thing, let me see if I can find this, that you could imagine in these flux tubes on the sun is that the magnetic field strength ramps up very, very rapidly at some point where the optical depth is around 1. And thus it turns all of the cosmic rays at about the same point in an energy independent way. Right. So if the magnetic field on a very small distance scale is strongly increasing, then all cosmic rays, regardless of energy, turn at about the same point. And so that's potentially one thing. And you could imagine, you know, cosmic rays that kind of skirt the surface. They get trapped in these tubes, they move up, and they just have multiple encounters at regions where they're slowly building up interactions with gas until they convert. But when they convert, they're still very close to the surface, and thus the gamma rays can escape. So that's a way of making the gamma ray emission and also the tau about 1. But you need to find these strong magnetic fields. And the magnetic fields have to be really strong once you're talking about 100 GeV gamma rays and TeV protons, right? They're, you know, this is not the best. Putting this in Tesla is not the best for my mental thought process here. But for a TeV proton, right, this is going to be something like a 3 kilometers at a Tesla magnetic field. And so for magnetic fields that are in the 100 Gauss range, which is, I think, kind of high end already for the sun, these are very long path lengths. And so keeping things trapped in this for a long time is difficult.
Okay, thanks.
Yep.
Thank you so much. I don't see other questions or hands raised. So, and thanks everyone for staying longer today. So if you want, there is still plenty of room for appointments with the speakers, so don't hesitate to sign up. With that, I think for today, I thank everyone, and we'll see you in 2 weeks because next week is spring break. See you soon. Thank you.